So we're talking about integral calculus. So what are a couple of things we've learned? If we wanted to find the area between a function like x squared and the x-axis between 1 and 4, we figured out a way of doing it by splitting this up into these really skinny rectangles. So skinny that they become straight lines, and we can get an exact, and we call it signed area because what we're doing is taking the height of the rectangle as the function value, and the width is a positive little width on the x-axis. But if f of x happens to be below the x-axis, that's going to give us a negative contribution to our signed area. But in this case, since x squared is always above the x-axis, if I want to get this area in between here, I can just add up an infinite number of skinny rectangles. Unfortunately, that takes a long time. It's a hard thing to do, but we came up with a fast way of doing it. The fundamental theorem of calculus says all we have to do is take the antiderivative of this function, plug in the two endpoints, and subtract them. And we even came up with a fancy way for representing what one of these infinite Riemann sums would look like. We'd say from 1 to 4 of the function dx. Now I'm going to use that fundamental theorem. I take the antiderivative, I plug in 1 and 4, and I subtract the two numbers. So I get 64/3 minus 1/3, or 63/3, or 21. So that would be 21 square units of area in between there, and that would be exact. It would also be the signed area, but really in this case we were just looking for the area. Now, what if we wanted a function? We didn't want a number, but we wanted a function that would give us the area between f of x and the x-axis, between 1 and any value of x you happen to plug into it. Well, since this finds it from 1 to 4, all we're going to do differently is make it from 1 to x. Now, any number we put in there is going to give us the signed area, but in this case the area, because everything is above the x-axis. So let's see what we get. And sometimes, you don't have to do this, but just to not be confusing between this x and this x, this is a dummy variable and this is a real variable, we sometimes write it with a different dummy variable. This really is what makes it a function of x. As you'll see, because the fundamental theorem would say, take the antiderivative, plug in 1 and x, and there goes the t's. So you get x cubed over 3 minus 1/3. And sure enough, this is the function that we're looking for that finds the area between 1 and x for any value of x. This one does it, but this one makes it a lot easier to just plug in a value of x. And we probably should check it. What would happen if we plug in 4? If we plug in 4, we get 64/3 minus 1/3, we get 21. So we get the same answer, which we would hope. So that's all kind of review. One thing we have never talked about, general antiderivatives of a function. We've talked about what they are. There are a whole family of functions that are antiderivatives of the function x squared. So that when you take the derivative of them, you get back to x squared. So since we haven't really got a symbol for this yet, we could make up anything. They could have done this. And that means take the general antiderivative. And the answer would have been x cubed over 3 plus c. But they decided not to use that symbol. Instead, they said, since antiderivatives have so much to do with signed area, we probably should use a symbol that kind of indicates that. And since we're using the integral sign to talk about signed area, let's use it to talk about antiderivatives. So this is what they decided to do. If you want to denote symbolically that I want to take the antiderivative of any function, you put an integral sign and a dx after it. No limits on our integration. That just means this is the general antiderivative. And what would it be? X cubed over 3 plus c. So now we no longer have to say, I want to find the general antiderivative. You just put it in there, like this. And it's even, since this general antiderivative is also now an integral, we should call it an integral. But it's not a definite integral like this one was. That's a definite integral. So we call it an indefinite integral. Just another name for a general antiderivative. Okay. So, then we could, all the antiderivatives that we know how to do yet, we can now put in this form. I can't say, find the general antiderivative of u to the nth. I can just say, this is what I want to find, the general antiderivative of u to the nth. And the answer would be, as we know, we've talked about these. Now you might ask, why am I using u instead of x? Well, you're going to see very shortly, because not all problems come out exactly the way you want it. You don't always find the general antiderivative of x squared. They're sometimes in the form of that, but not exactly in that form. And we're going to try to get them into that form. So we could have picked any letter, but usually if you're looking at formulas, general antiderivative formulas, we use u as our variable instead of x. It would be true if I put x to the n here, that this would be x to the n plus 1 over n plus 1 plus c. And we know these other antiderivatives. The cosine of u is the sine of u. The sine of u is minus the cosine of u. The general antiderivative of secant squared is the tangent of u. Cosecant squared is, it's so it's minus, and it's just like, cosecant is just like secant, so it's, except it's so it's cotangent. Just a way of remembering it. Mostly these are just memorization. The derivative of secant of x is secant of x tangent of x. So the antiderivative of secant of u tangent of u is secant of u. And then here's another so it's going to be negative, and it's just like this one, except it's so it's cosecant squared of u. So these are the only antiderivatives that we really know how to take so far. By the end of the year, it will go up to 12 or 13, and that's all you really need to know. So, just wanted to throw this in there. Which of these three answers would be the general antiderivative of this function? That could be a question that you had. In other words, it's a multiple choice question. Can you find, and again, I don't have to say words. I can just say find this, and I know I'm looking for the general antiderivative of this function, x cosine of x. Well, you can see that none of these are u cosine of u. So you could say, I really don't know how to do it. In fact, you aren't really going to learn how to do that this year. That would be something done in a Calc 2 class. There's a technique you could do that. But could you answer the question right now? And that's why I'm proposing this problem. And the answer is yes, because it's multiple choice. So what do we know? If this really is the correct answer right here, then we should be able to take the derivative. If this really is the antiderivative of this function, we should be able to take its derivative and get this. So let's try it. What's the derivative of x sine of x plus c? The product rule says it's the first times the derivative of the second plus the second times the derivative of the first, and then the derivative of a constant is 0. Well, it didn't quite work. We didn't get x cosine of x. We've got an extra sine of x. Well, let's try this one over here. What's its derivative? We already know that it's x cosine of x plus sine of x. But now we have to go minus the derivative of the cosine of x. And the derivative of the cosine of x is minus the sine of x. So it still doesn't quite work. But I think you can see now, because this one is just, the only difference from this one is it's plus, this would just be minus, and they would cancel out, and sure enough, we get it. So we would know that that would be our answer. So sometimes you can do a problem, even though you can't start from here and be able to get the right answer, you can check which one of these would be right, knowing that the derivative of an antiderivative would be the function. Okay, so given that we've only got 7 antiderivative formulas, and we'd like to be able to take antiderivatives of so many formulas, just like with derivatives, we're going to find some other rules that are going to help us. Unfortunately, there isn't any product rule. And we really don't even have a chain rule. But we have something that works a little bit like a chain rule. And it's going to be called a U substitution. And that's why I wrote all these formulas in terms of U. And like I said before, any letter could have been used. But the goal is, since we only know these 7 formulas, we have to get the problem we have into one of these forms. So let's shift over to the other board here. Keep these formulas in mind, and let's go to this first one. Does that look like any of those 7 forms? No, but in my mind, I can think I might be able to get this into the form of u to the 1/2 power du. To do that, I'm going to let u equal 4x minus 1. Now, why would I do that? Because now I can rewrite, instead of putting this, I can write u to the 1/2. But I don't want to have u to the 1/2 dx. So I have to find out the relationship between dx and du. So we're going to do something we haven't done in a while. We're going to take the differential. We're going to take du. Well, if you remember, du is equal to f prime of x dx. Well, the derivative of this is 4. In other words, it's sort of like saying du dx, the derivative of u with respect to x is 4. So du is equal to 4 dx in differential form. Well, we have to somehow replace this dx. So looking at this, what's dx? It's 1/4 du. And I can take the 1/4 out front. And now we've got it into one of those 7 forms. U to the nth du. So the antiderivative is u to the n plus 1 divided by n plus 1, so it would be times 2/3 plus c. So your final answer would be 1/6. And you don't want to leave your answer in u. This is a problem in x. So we put back what u was. And now we've got our answer. We took something that wasn't in one of those 7 forms and got it into the correct form so that we could take the antiderivative. And we kind of knew, since there wasn't any trigonometry functions in here at all, trigonometric functions, we knew it had to be that first form if we could do it at all. Well, let's proceed on to the next one. Which one could this one possibly be? I'm thinking sine of u du. We kind of have to use our imagination a little bit. I can imagine this to be u. So if I can imagine that, let's write it down. Say u is 2x squared plus 5, so du is going to be the derivative of this times dx. And now I can try to rewrite what I've got up here. Instead of sine of this, I'm going to write sine of u. And what's left, I've already taken care of that. I have x dx. Well, look back here. What is x dx? With a little bit of algebra, you can see x dx is 1/4 du. So I can put 1/4 du. And I've got it exactly in the form that I want. The antiderivative of sine of u du is minus the cosine of u plus c. So your last step is just to get it back into the form you want. You don't want a u there, so you put 2x squared plus 5. And there is your answer. So that is our second u substitution. Now this next one, number 3, looks like it's got trigonometric functions in it, but I don't think there's any of those 6 forms you could get that into. You can't get it into the form of sine of u du. And a lot of this is just going to take practice, and sometimes you have to just try something. Well, I'm thinking if we let u be the sine of x. Why would I think of that? Because the derivative of the sine of x is the cosine of x, and that's what's sitting there. So if I go du, I just get cosine of x dx. And when I rewrite it, this I can call u, and the cosine of x dx is just du. This one was easier than the other ones. This is now in the form of u to the nth du. You don't really see the n there, but it's really 1. So the antiderivative is u squared over 2 plus c. And then you just put back what u was, the sine of x. And that would be a perfectly good answer. probably if you write it that way, that would be more recognizable to more people. Okay, let's see if we're starting to get the hang of these. When I see cosine to the fourth of x, I'm thinking u to the fourth du. And by the way, this is a definite integral, so we're going to have to also do something about these limits. So let's first let u equal cosine of x. I'm going to do that because now I can take all of this and just call it u to the fourth. The 5, I can just put out front. And what's left? Sine of x dx. Well, du is what? Minus the sine of x dx. Almost what we've got here. So that means that sine of x dx is just minus du. So I can just put a minus sign and a du. And I've taken care of everything inside our integral. But I still have to take care of these limits. Remember, these limits are x equals 0 to x equals pi over 2. Well, I'm doing it in terms of u. So what do I know? If x is equal to 0, u is equal to the cosine of 0, which is 1. And if at pi over 2, the cosine of pi over 2 is 0. So now we've completely transformed it into another definite integral, which is going to be a number, and that's what we want. So we're never going to have to actually transform this back into x. We just do our fundamental theorem. What's the antiderivative of u to the fourth du? U to the fifth divided by 5, which you can either leave in here or bring out front. So we're left with negative 1 times 0 minus 1. So the whole answer to this definite integral is a big 1. I'm hoping you're seeing that from only knowing 7 fairly simple formulas, we're able to do a lot more integrals than we ever thought we were going to be able to do today. And doesn't this one look pretty complicated? So what could I do? I can think of, there's no trigonometric functions in here, so I'm probably going to have to get it into the form of u to the nth du. And this is what I see right here, especially since it's below the division bar. If I let u be 1 plus x to the fourth, then I can call everything, including that division bar, I can call it u to the negative 1/4. I've got that u to the nth. I can take my 6 and just bring it out front. Now, you always end up having to do du. Du is what? 0 plus 4x cubed dx. Well, we don't have 4x cubed dx, we have x cubed dx to deal with. So if you look at it algebraically, what is x cubed dx? It's 1/4 du. And now you've done your transformation. So 6/4 is 3/2. The antiderivative of u to the negative 1/4 would be u to the, goes up by 1 to 3/4, then divided by 3/4, or times 4/3. and then your plus c. So you get 2. Now you put u back in there. U is 1 plus x to the 4th to the 3/4 power plus c. And you've got an answer. So let's end this off with one other one that's got secants and tangents, and boy, this is going to be tough. And we're not using x, we're using a different variable this time, t. That shouldn't bother us. I'm not sure exactly where to go, but I don't have too many choices. So let me just try to let u be tangent of t. Let's see if that works out. Why would I even think that? Because I know the derivative of the tangent is the secant squared, and that's sitting right there. So du is secant squared of t dt. So if I rewrite this integral, I can call tangent of t u and secant squared of t dt du. So it turned out to be fairly easy. I can just get u squared over 2 plus c. And u is the tangent, so it's the tangent squared of t over 2 plus c. Now, sometimes there's more than one way to do it. What if I hadn't thought of letting u be the tangent of t? What if I let u be the secant of t? What would du be? Du would be secant t tangent t dt. And when I rewrite it, one of these secants would be the u. And what would be left would be secant tangent, which is du. You get the same thing. You get u squared over 2 plus c. Except now u is the secant of t. So we get secant squared t over 2 plus c. Uh-oh. They're not the same answer. Did we do something wrong, I wonder? Well, I think if you get out your graphing calculator and you graph this function and this function, you find out they're not the same. But they look identical, except one is just shifted up and down on your graph. So that's taken care of by this plus c. Because that plus c just shifts the graphs up and down. So you get the same family of functions in both cases. So, anyway, that gives you a good idea of what u substitutions can do to take memorizing 7 basic formulas and then being able to do lots and lots and lots of more integrals. So, hope that makes you happy, and hope to see you the next time.